Got the first section on Hospital's rule. Do you want me to go over that, or are you okay? Okay, I'll do... let me do the first problem in each section, I guess. Okay. Okay, now I'm gonna mute you temporarily because I'm getting a lot of feedback and I can't really hear what's going on, so... just unmute yourself whenever you have a question, okay? Alright. So this first one, I'm plugging in 0 from the right, so I'm going to go ahead and plug in 0 first. If I plug in 0, then I'll have the tangent at 0 up on top, and I'll have the sine at 0 here. Now, if I do, the natural log at 0 does not exist, but the natural log at 0 plus a little bit would be negative infinity. If I graph a natural log, it would look something like this, where the natural log of 1 is 0, and the natural log of 0 is undefined. But we have sort of asymptotic behavior, so it acts like a vertical asymptote at x equals 0. So the closer and closer we get to x equals 0, the closer their natural log is going to get to negative infinity. So right now, if I plug all of this in, we'll get something like this. So plugging in 0, I would have 3 ln of the tangent at 0, which is 0, over the natural log of the sine at 0, which is also 0. The natural log at 0 plus a little bit would approach negative infinity. So this is 3 times negative infinity over negative infinity, which is undefined, but does allow us to use Hospital's rule. Any questions so far, just on plugging stuff in? Okay, so with Hospital's rule, if you end up with a function that is 0 over 0, or positive or negative infinity over infinity, then I can derive the top and the bottom of your fraction separately and plug in our number again to get our answer. So I'm going to do that really quick. So this is Hospital's rule. Means that this limit should be equal to the same limit, the limit at x approaches 0 from the right, of the derivative of the top divided by the derivative of the bottom. The derivative of the top, our 3 is a constant, so that's going to stay the same, but if I derive the natural log of something, I'll get 1 over something times something prime. So if I derive natural log of tangent x, I should get 1 over the tangent of x times the derivative of tangent, which is the secant squared of x. On bottom, I've got natural log of sine x. So when I derive that, I'll get 1 over the sine of x times the derivative of sine, which is cosine x. Okay, any questions on our derivative part? Okay, again with Hospital's rule, we're not using quotient rule, we're deriving the numerator and denominator separately. As long as you get 0 over 0 or positive or negative infinity over infinity, then our limit will be equal to the limit at the same value of the derivative of the numerator divided by the derivative of the denominator, is Hospital's rule. Okay, so I've got our first derivative here. So now I'm going to simplify things a little bit, and then once I've got this simplified, we'll go ahead and plug in 0 plus a little bit and see what happens. On top, I've got, I think I'm going to rewrite everything in terms of sine or cosine, just so you can see what's happening here. So I've got 1 over the tangent of x. Tangent of x is sine over cosine. So I'm eventually going to flip that in the next step, because 1 divided by a fraction means we can just flip the fraction. Secant squared. Secant is 1 over cosine, and I've got 2 of those. This is really 1 over cosine squared. Okay, divided by cosine over sine. Cosine over sine. Okay, everyone okay so far? I've rewritten all of our tangent and secant into sine or cosine. I'm going to keep simplifying so that sines and cosines start canceling. And next step. Okay, for my next step, I've got 1 divided by a fraction, so I can flip and multiply. So this will be 3 times cosine x over sine x times 1 over cosine x. I don't need to change. 1 over cosine squared x. Okay, and then on bottom, I'm dividing by a fraction again, so I can flip and multiply. So I'm going to multiply the whole thing by sine x over cosine x. Okay, now I'm ready to start canceling stuff to see what happens. I do still have our limit, which I didn't write in the last one. It's just the limit as x approaches 0 plus. I haven't plugged that a point yet. The limit as x approaches 0 from the right. Okay, so I'm going to go ahead and cancel. We'll keep going from there. So Kyle, I'm going to start with you. What can cancel?
Cosine, the first cosine, sine, and sine over cosine.
Okay, cosine, sine, sine, cosine. Okay, so that leaves me with 3 over cosine squared. And then Niall, what is the cosine at 0? If I plug in 0 plus a little bit right now. Yes, what's the cosine at 0? Okay, I've got a lot of noise again, unfortunately, so I couldn't really make that out. I apologize. So my cosine at 0 is 1. So from our unit circle, cosine is my x value, and at 0, everything is my x value, so this would be 1. So when we go ahead and plug in 0 plus a little bit, this will be 3 divided by the cosine squared at 0, which would be 3 divided by 1 is 3. Okay, any questions on this one? Zoom out a bit so we can see the whole problem. So for all of these El Hospital rules problems, what you're going to need to do first is try to plug in your point. If you can plug in your point and actually get an answer, stop there, that's your answer. But if you get either 0 over 0 or plus or minus infinity over infinity, then you'll have to use El Hospital's rule, which means you'll have to derive the numerator and denominator separately and then plug in your point again. You can make any cancellations you want to simplify after you derive, like I did here. But that should let you get the right answer. If you end up with 0 over 0 or positive and negative infinity over infinity again, you can always keep doing that process, so derive again. Okay, any questions on the first section, El Hospital's rule?
Mr. Clarification.
Go for it.
So we only derive the right side of both the numerator and denominator, or the right side.
Okay, so I'm deriving the entire thing. I'm deriving the numerator and denominator separately for the whole fraction. So here's my whole fraction here. If I derive 3 ln x, 3 is a constant multiple, so my 3 is going to stay the same. But when I derive ln x, I'll get 1 over x times x prime, right? So in this case, my inside part, that x is really tangent x. That's 1 over tangent x times tangent x prime, which is secant squared x. No problem. Okay, that's probably the hardest part of this. I've also got some limits down here. Every handful of these is testing a different skill, I think. Is there anything that you guys wanted to go over? Any number that looks particularly hard? Which one? 10 and 11. Okay, so both of these have e to the x. I'm going to go over one of them because I want to leave one for practice, since they're both the same skill. I think every 2 problems is pretty much the same skill. Okay, so pick one. Do you want to do 11 or do you want to do 10?
10 sounds great.
Okay, cool. I agree, 10 looks a little harder. So for this one, I've got a fraction here. I could cheat since we've got our growth rate rules. Do you remember factorials grow faster than exponentials? So that's the x, where a is a real number. Grow faster than polynomials. That's x to the n. Grow faster than logarithms. Grow faster than sine or cosine. Just grow faster than a constant. Okay, so this is where a is a constant and x is a variable. I'm going to replace this n with an a, actually. Okay, so we had an acronym in pre-calc: feed elephants peanuts, love someone cool, showing which growth rate is faster. So right now, my fastest growth rate for this fraction is actually e to the x. So if this fraction is growing fastest on bottom, then what will it approach if we plug in infinity? If the bottom of my fraction grows faster than the top, then what will happen to this term? Anyone? So right now we said exponentials grow faster than polynomials. I've got an exponential on the bottom, and I've got a polynomial on top. So for this fraction here on the left, the bottom is growing faster than the top. So if that's true, what will this fraction approach as x gets close to 0? Not negative infinity, no.
Yeah, I think it's
Okay, so it is 0. Let me explain why really quick. So as an example, for something that's growing faster on bottom, so this time I'm going to grow the bottom of the fraction, but I'm going to leave the top the same, just so you can see what happens. So 1 over 1, 10, 1 over 100, 1 over 1000. Okay, what's happening to my fraction? Is it getting bigger or smaller? Way smaller, yeah. So if we're growing faster on bottom, then we'll approach 0. If I was growing faster on top, then the opposite would happen. So if I'm growing faster on top, it would look like this. Okay, then I'm approaching infinity. If we're growing at the same rate, then I'll approach the fraction of our coefficients. I'll give us a couple more examples for this in a second. But let me finish this problem off before I leave it. Okay, so for this one, we said this whole fraction is approaching 0. So if this whole fraction approaches 0, then this is really 0 minus 2 is negative 2. Okay, let me generate a couple more. Okay, so for this one, just realized now I'm not going to be able to annotate this, I don't think. So let me grab a screenshot. Okay, so for this one, I'm going to look at my largest terms on the top and bottom first. Is my largest power on top or on bottom or both? Okay, Kyle, which one's growing the fastest? The top, the bottom, or are both growing at the same rate? Okay, both at the same rate, you're right. And we'll show that really quick. So if we simplify this, the square root is going to cause this first term to approach 2t plus something. On bottom, I've got 4t plus 3. So that means both the power of my first terms are going to be the same after we take that square root. Because we only care about the largest term, even though we don't know exactly what the square root of 4t squared plus 1 is, we don't care, because our growth rates only depend on our largest term in the numerator and denominator. Okay, just flashed. You guys still hear me? Okay, cool. So I do have the same power on top and bottom. That means we will approach the fraction of our coefficients. Niall, what's the fraction of my coefficients?
divided by 4t plus 3 divided by t.
I think you're deriving this right now, right? You're using L'Hospital's rule?
Oh,
Is that what you're doing?
so I'm not sure.
Okay, you can do that. That'll work. I'm gonna shortcut though, because we're approaching infinity or negative infinity for our point. We can just look at growth rates, so we should be able to solve this problem that way. So right now, because our growth rates are the same, when you take the square root of 4t squared, we end up with 2t. I will approach the fraction of my coefficients. So for this one, I should be approaching 2 over 4 is 1/2. But I do need to worry about what's happening with my sign. And that's because when you plug in a negative infinity here into this t squared, that negative will become a positive, right? Okay, then we took the square root of a positive number, it would still be a positive. But on bottom, when we plug in negative infinity, that would be a negative. So right now I've got a positive divided by a negative, which should give us negative 1/2 for our final answer. Okay, any questions on what I did for this one? I'm going to go back and try to solve this Niles way next. So, yes.
How does the top become a positive element?
So if I walk through the steps here, we would have plugged in a negative infinity here into this t squared, right?
Oh, okay.
Right. Before we actually took that square root, we squared it. So even though I did simplify that to just t here, we've actually already squared that negative infinity before I got to this step. Okay. Niall, are you okay with this one?
Oh, yeah.
Okay. I am going to try to solve this through L'Hospital's rule, since that's what you were doing earlier. So let me do that really quick. So same problem, different method. If I wanted to solve this with L'Hospital's rule, this is the limit as t approaches negative infinity of the square root of 4t squared plus 1 over 4t plus 3. Okay, if I plug in negative infinity right now, I'll have negative infinity squared is positive infinity times 4 plus 1 is still positive infinity. Underneath the square root is still positive infinity on top. On bottom, if I plug in negative infinity, this would be 4 times negative infinity is negative infinity plus 3 is still negative infinity on bottom. So I have negative infinity over infinity, which means I can use L'Hospital's rule. This limit should also be equal to the limit as t approaches negative infinity of the derivative of the numerator. So that would be, rewrite this really quick, that square root is the same thing as raising something to the 1/2 power. So when I derive this, this will be 1/2 times 4t squared plus 1 to the negative 1/2 power times 8t divided by 4. Is everyone okay on the first step? Okay, I'm going to keep going then. So I've got a 1/2 here. So this 2 I can move to the bottom of the fraction. Will give me 2 times 4 is 8. I've got an 8t on top here. This is a negative 1/2 power, so I can move this whole part to the bottom of the fraction to make it positive is 4t squared plus 1 underneath the square root. I'm still taking the limit as t approaches negative infinity. My 8s will cancel. That leaves me with t over root 4t squared plus 1. Taking the limit as t approaches negative infinity. Okay, the problem here is, even though we've reduced this with L'Hospital's rule, right now if I plug in negative infinity, I've still got my rules for solving limits at infinity that are going to come into play, so I don't think this has made it any easier. If I plug in negative infinity right now, I'll have negative infinity on top. On bottom, I'll have the square root of 4 is 2 times negative infinity squared is positive infinity. Squared underneath the square root is positive infinity plus something is still negative infinity over infinity. I could technically do L'Hospital's rule again. I don't know if this is going to simplify to something that I can solve without our limits at infinity rule. So I'll try it one more time and we'll see. But if it is one more time, I've got the derivative of the top is 1. The derivative of the bottom is 1/2 times 4t squared plus 1 to the negative 1/2 times 8t, which we can simplify to this negative 1/2 means I can move this to the top of the fraction, is 4t squared plus 1 underneath the square root on top now, over 4t on bottom. So we still haven't been able to solve our problem of having a t in both sides, unfortunately. So I think we're going to be stuck in an infinite loop here. So we're almost back to what we were originally. Where I've got that same part over 4t. If I derive that, I'm going to end up back to really similar to what we had last time. Where our powers will end up being the same. So I think L'Hospital's rules is going to throw you for an infinite loop in this one. We'll need to use what happens when we plug in limits at infinity or negative infinity for our rules at some point in order to solve this. Yes.
Is there a no calculator section on calculus AP practice BC?
Yes. So half of your test is without a calculator and half of your test is with a calculator. Assuming that they actually do the full version of the AP exam this year, you guys will have something that looks like this. So you have a multiple choice section. Without a calculator. Multiple choice section with a calculator. A free response section with a calculator, which is 2 questions. A free response question without a calculator, which is 4 questions. Each of your free response question take 15 minutes. So this is 60 minutes and this is 30 minutes. For your multiple choice, I believe this is a 45-minute section and a 55-minute section. Yes.
For the FRQ section without the calculator,
What are the concepts that are tested the most? All of calculus BC boils down to limits, derivatives, or integrals, or sequence and series, which is really just more integrals. But it's going to test one of those three things: limits, derivatives, or integrals. We've seen some of the Fourier response earlier, so things like rates of change, things like what else have we done so far? We've done curve sketching. So we saw FRQs from those in pre-calculus that were on either the AB or the BC exam or both. The reason why we call it calculus AB and calculus BC is because there's some overlap in your content. In practice, usually 3 of the questions that are on the AB exam are also on the BC exam for your Fourier response questions. Now that doesn't directly answer your question, but can show you a sample for your response if you want. Right. Untitled Chapter. Okay, so these first 2 are with a graphing calculator. So we've got a rate of change question. Okay, the second one is sort of an integration and accumulation question. Where we're looking at a little bit of particle motion down here, finding the total distance traveled, and then explaining what our integrals and derivatives of this function would mean in context. Okay. Here I've got a piecewise function without a calculator that we can break down into some basic shapes. So that's rectangles, triangles. I do have a curve here. That's a curve that we could integrate if we need to, since we're given the function for it here. And they want us to answer some questions about what the integral or the derivative would be of both this function and the composite function. G is the derivative of f, and we're given values for f to start out with. It's very similar to what you guys did in the graphical integration problems that you did in pre-calculus. We're just let me go back, adding one more layer of complexity to it, in that sometimes we're talking about f, which is not what's graphed. If g is the derivative of f, then f would be the integral of g. Okay. Here I've got a Riemann sum approximation as part of this. We've got a model that we're using for rates of change. We're explaining what these derivatives of this model would mean. Here I've got something we haven't learned yet, where we're integrating, instead of integrating a function, we're integrating 2 different equations. This is a polar equation, which we'll talk about later on. That's just getting the area between 2 curves with a bit of a twist. And this is a sequence or series problem we also haven't learned yet. Calculus AB does not do any of the polar or parametric stuff, so that means stuff that are not functions. Calculus AB also does not do any of the sequence or series stuff, which is the main difference between AB or BC. Other than that, we cover the same content. Does that answer your question? Yeah, okay. Okay, so I'm being told we've got 10 minutes before this is going to kick me off Zoom. If it kicks us off, I'll just do another call. So just rejoin at the same link. Okay, were there any other questions that you guys wanted to go over from the homework? Which number? Okay, so this is a piecewise function.
I have a number. I got a constant, but according to the answer sheet, it does not exist.
Okay, so first we're getting a general limit. My limit is x approaches -1. In order to have a general limit, we have to have both of our one-sided limits approach the same value. So that means the limit as x approaches -1 from the right must be the same as what happens when we approach x equals -1 from the left. If they're not the same, then our limit does not exist. So I'm going to test both, and we'll see if they're the same or not. Okay, first, the limit as x approaches 1 from the right of f of x. If I am, sorry, -1, not +1. -1 from the right. So that would be something like -0.999999, repeating. So in that case, we are a little bit greater than -1, so I'm going to plug into the bottom of my fraction. So if I plug in -1 into this fraction, this equation, I'll get this, -1 minus 2. -1 is +1, minus 2 is -1. On the opposite side, if I approach -1 minus a little bit, -1 minus a little bit is a little bit less than -1, so I'd use the top function. If I plug in -1 into the top function instead, I'll get 2 times -1 is -2, plus 7 is 3. So my one-sided limits do not match. And because my one-sided limits do not match, the general limit as x approaches -1 of f of x does not exist. Welcome back. Okay, so the key to this one is our one-sided limits did not match. My limit from the left was 3, my limit from the right was -1, so my general limit cannot exist. Oh, I think I've lost your audio. Can you hear me? Hey. Okay, so cool on this one. Okay, welcome back now. Okay, now are you okay on 8?
Yeah.
Okay, anything else from the worksheet?
Bless you.
Thank you, you too. All right, I'm going to pull one of these last 4. These last 4 on the worksheet are all formal definition of derivative problems. You could also solve them by L'Hospital's rule, now that you know L'Hospital's rule. Let me pull one of these trig functions really quick. So we'll do 16. If I want to solve this using the formal definition of a derivative, the formal definition of a derivative says the limit as h approaches 0 of f of x plus h minus f of x over h is equal to the derivative of f of x. Using that, right now my function is 3 times the sine of my x value. So I could say f of x is 3 sine x. And my x value is 5/6. We can check because 3 times the sine at 5/6 should be what I have here. That's my function of x. The sine at 5/6 is 1/2. 3 times 1/2 is 3/2. This is 3 sine 5/6. Because this is in the formal definition of a derivative form, we should be able to just derive this function, f prime at x is equal to 3 cosine x, and then plug in my x value to get our answer, 5/6. So this is 3 times the cosine at 5/6. Write like this, because that's too many parentheses. So 3 times the cosine at 5/6. The cosine at 5/6 is -√3/2. This is 3 times -√3/2 is -3√3/2. For our final answer. If you don't like that, you could use L'Hospital's rule to solve this instead. Since if I plug in 0, you'll get 3 sine 5/6, which, since we already said our right term is also 3 sine 5/6, is the same thing minus the same thing is 0 over 0, which means I should be able to derive this and get the same answer. And if I do, you'll get 3 times the cosine of 5/6 plus h over 1, which when we plug in, h approaches 0, will be 3 times the cosine at 5/6, which is exactly what we had here. Again, cosine 5/6 is -√3/2. -√3/2 times 3 is -3√3/2. L'Hospital's rule can shortcut for a lot of your limits, but you have to know how to derive stuff first before you can use it. Any questions on this one? Okay, I think you guys are good on all of this then. At least we seem to be out of questions. Did anyone have any trouble with the unit circle part? So that was the stuff from last week. Unit circle was fine, okay. Alright, well, if you guys don't have any more questions, then thank you so much for coming, and I can see you guys again next week if you want to come.
Oh yeah, I have one last question.
Oh, go for it.
What's the growth rate of tangent?
Unfortunately, tangent doesn't have a direct growth rate. And the reason why is because when you graph tangent with a function that's kind of asymptotic, looks like this. So unlike sine or cosine, it doesn't just bounce. Those asymptotic, so it's like pi over 2. Since tangent is sine over cosine, the cosine of pi over 2 is 0. And negative pi over 2 as well. If you get really, really close to pi over 2, from the left, you'll approach positive infinity. From the right, you'll actually run into the next repeat of tangent. And the next time that... So if you had the limit as we approached pi over 2 from the right, your answer would be negative infinity. If we approached pi over 2 from the left, your answer would be positive infinity. If you wanted a general limit at pi over 2, it does not exist because your one-sided limits are not the same. Let me do the rest of 13 then. So this one... I think I'm frozen, so I'm going to take a screenshot and move over to Word really quick. Close stuff we don't need. I think I'm running out of RAM. There we go. Okay, back over to Word. Nope. Unfrozen? Can I erase? Nope. There we go. Okay, so if I plug in 0 into the top, the tangent at 0 is 0. And then 4 times 0 is also 0, so I've got 0 over 0. So that means we can use L'Hospital's rule. If I use L'Hospital's rule, what's going to happen to the top? Okay, the secant squared. And what happens to the bottom? Becomes 4, okay. So this is really 1 over 4 times 1 over cosine squared x. What is the cosine at 0? 1. Okay, so this is, the cosine at 0 is 1, squared is still 1. So this is 1 over 1 times 1 over 4. It's still 1 over 4. Still having technical hiccups with Edge, but any other questions before I go? Okay, go for it.
Like a while ago, I was solving the problem. That was about derivative and limit. Basically, so like alpha, like one of the problems I found hard was no one in the
One with the cubed root. I don't see it. Which number?
like
Or not on this?
like
Okay, so make up a problem for.
wow.
Okay, make up a problem for all hospitals roll with the cubed root. Sure. Limit as x approaches. We'll do 0 of sine x over the cubed root of x, maybe? Is that okay? I'm just making up a problem, but so is this what you're looking for? Something like the limit is x approaches 0 of the sine of x over the cubed root of x?
Or can I say the problem?
Yeah, go for it.
So that's the limit h to 0
Okay.
is the cube root of 5 plus h. Negative cube root of 5
Over h?
over h.
Okay. So first, two ways you can solve this, either a hospital's rule or a formal definition of derivative. I know I can use formal definition of derivative because I've got the function of my x value plus h over here, and I've got a function of x over here, dividing by h as h approaches 0. So do you want to solve this using Al Hospital's rule or the formal definition of derivative?
Can I take both?
Sure. So okay, so for the formal definition of a derivative, says f prime x will be equal to the limit as h approaches 0 of f of x plus h minus f of x over h, which is what we have here. I've got a function of x plus h, my input is x plus h, and I've got another function here where my input is x. And the action that we're doing to those are the same. I'm taking the cubed root. So I can say f of x right now is equal to the cubed root of whatever our input is. If that's true, the cubed root of x is x to the 1/3 power. So f prime x will be 1/3 x to the negative 2/3 power. My x value right now is my original input is 5. So I'm going to plug in 5. F prime at 5, it's a little bit darker, is 1/3 times 5 raised to the negative 2/3 power. And we can simplify if we want. So that's 1/3 cubed root of 25. With the hospital's rule, if I plug in 0 right now, I will get the cubed root of 5 minus the cubed root of 5 on top is 0 over 0. So that tells us we can use the hospital's rule. If I derive the top, we'll have 1/3 times 5 plus h to the negative 2/3 power. If I derive the bottom, I'll have 1. I'm going to take the limit as h approaches 0 of the whole thing. If I plug in h is 0 here, I'll get 1/3 times 5 to the negative 2/3 power, which is the same thing as 1/3 times 1 over 5 to the 2/3 power, which is 1/3 times 5 squared is 25. Underneath the cubed root is the cubed root of 25, which is the same thing that we had here. Any questions on what we did? Unmute you really quick. Okay, Niall, any questions? Okay, cool. I'm going to break there. Just want to give my neighbors a chance to sleep, but thank you guys very much for coming. I might hold office hours a little bit earlier next time, just so I don't have this problem. All right. Goodbye, see you next week. If you guys have more questions, feel free to hit me up when we chat.